You know, there's a compelling narrative that appears throughout science fiction and scientific speculation about advanced civilizations and in serious discussions about the Fermi paradox. The idea that sufficiently advanced technological species will eventually develop interstellar travel capabilities, allowing them to spread throughout their galaxy, colonizing star systems and establishing presence across thousands or millions of light years. That this galactic expansion is the natural destiny of intelligent life and represents the ultimate expression of technological mastery over nature. That civilizations like humanity will someday build spacecraft capable of crossing the vast distances between stars at some fraction of light speed, carrying colonists to new worlds orbiting distant suns. This vision suggests that the galaxy should be teeming with advanced civilizations that have spread from their origin worlds to occupy substantial regions of the Milky Way, creating networks of colonies connected by trade and communication and genetic exchange across interstellar distances. The narrative is supported by apparently reasonable extrapolations from known physics, showing that relativistic travel approaching significant fractions of light speed doesn't violate any fundamental laws. Calculations demonstrate that spacecraft could theoretically be accelerated to 0, 1c or 0, 5c or even 0, 9c. Using various propulsion concepts like fusion rockets or antimatter drives or laser-pushed light sails at these speeds, crossing the galaxy's 100,000 light-year diameter would take anywhere from thousands to hundreds of thousands of years, long by human standards, but short compared to evolutionary or geological timescales, suggesting that patient civilizations could accomplish galactic colonization over timescales of millions of years, which is trivial compared to the billions of years that galaxies exist. This reasoning is used to sharpen the Fermi paradox. If interstellar travel is physically possible, and if intelligent life has arisen multiple times in our galaxy's history, and if technological civilizations naturally expand across the galaxy given enough time, then where are all the aliens? Why don't we see evidence of galactic-scale civilizations in the form of megastructures or altered stars or radio signals or visits to Earth? The absence of observed aliens, despite the apparent inevitability of galactic colonization, creates the paradox that has generated enormous speculation about solutions ranging from "we're alone in the galaxy" to "civilizations destroy themselves" to "aliens are hiding from us" to "we're living in a simulation." And I'm going to tell you why the foundational assumption of this entire discussion is wrong, and why understanding this transforms how we think about the Fermi paradox and our place in the universe. It is impossible for any biological species to cross the galaxy using any remotely realistic technology or mission architecture. Not impossible in the absolute sense that it violates fundamental physics, but impossible in the practical sense that the distances and timescales and energy requirements and radiation exposure and reliability demands and biological constraints create insurmountable barriers that no biological civilization can overcome regardless of technological advancement. Galactic travel kills everything. Any biological organism attempting to cross significant portions of the galaxy will die from cumulative radiation damage or system failures or biological aging long before reaching destinations thousands of light years away. The distances are so vast and the timescales so extreme and the hostile environment so deadly that biological organisms cannot survive crossing interstellar space at scales necessary for galactic colonization. Even traveling at substantial fractions of light speed, which itself requires overcoming enormous engineering challenges, the journey times remain measured in thousands to millions of years, during which cosmic radiation steadily destroys biological tissue, spacecraft systems degrade and fail, and even if organisms are in suspended animation or frozen, the damage accumulates relentlessly. There is no shielding adequate to protect biology from high-energy cosmic rays over such timescales. There is no engineering that can maintain complex systems functioning reliably for millennia without maintenance. There is no biological preservation that prevents radiation and time from destroying cellular structures. Now, let me be extremely precise about what I mean by impossible for any species to cross the galaxy, because this is a strong claim that requires careful definition to avoid confusion. I'm not claiming that sending small robotic probes across the galaxy is impossible, or that transmitting information via electromagnetic signals is impossible, or that some hypothetical post-biological artificial intelligence couldn't spread through the galaxy. These might be possible, though still extraordinarily difficult. What I'm claiming is that biological organisms, meaning any form of life based on chemistry and cellular structures and metabolism, cannot physically survive the journey across significant portions of the galaxy, meaning distances of thousands to tens of thousands of light years. When I say galactic travel kills everything, I mean that the combination of cosmic radiation exposure, spacecraft system degradation, and biological decay over the extreme timescales required for galactic crossing creates absolutely certain death for any biological organism attempting the journey. The probability of biological survival approaches zero, not because of any single insurmountable barrier, but because of compounding factors, each of which alone would be extraordinarily difficult and together create mathematical certainty of failure. You might survive 1,000 years of cosmic radiation, or you might survive 10,000 years of system degradation, or you might preserve biology through 1 million years of freezing, but you cannot survive all three simultaneously over the timescales required for crossing thousands of light years. The fundamental reason why galactic travel is impossible for biology is the combination of vast distances and fundamental speed limits, creating extreme timescales during which unavoidable radiation and decay processes destroy biological systems. The distances between stars and the galactic disk average about 5 light years, but the distances to interesting destinations like Earth-like planets orbiting Sun-like stars might average hundreds to thousands light years because such systems are rare, even traveling at 0-1c, which would require enormous energy expenditure and revolutionary propulsion technology. Crossing 10,000 light years takes 100,000 years, during which cosmic radiation delivers lethal doses thousands of times over, and spacecraft systems fail catastrophically, and biological preservation fails. Let me start by examining the distance and timescale constraints in detail, because these create the fundamental framework within which all other challenges operate. The Milky Way galaxy has a diameter of roughly 100,000 to 120,000 light years and thickness of about 1,000 light years in the disk where most stars reside. The Sun is located about 26,000 light years from the galactic center in one of the spiral arms. These distances are so vast that they're almost incomprehensible in human terms. 1 light year is about 9.5 trillion kilometers, or roughly 63,000 times the distance from Earth to Sun. The distances across the galaxy are measured in hundreds of thousands of trillions of kilometers. The number of stars in the Milky Way is estimated at 200 to 400 billion. These stars are distributed across the galactic volume, with average separation in the disk of about 5 light years between neighboring stars. But this average is misleading because stars are not uniformly distributed. Stellar density is higher near the galactic center and in spiral arms, and lower in interarm regions. The nearest star system to our Sun is Alpha Centauri at 4.4 light years, but the next nearest stars are Barnard's star at 6 light years and Wolf 359 at 7.9 light years. And there are vast regions with no stars for tens or hundreds of light years. If we're interested in galactic colonization, the relevant question is not just the distance to nearest stars, but the distance to stars with potentially habitable planets. Not all stars are suitable for hosting life-bearing planets because very massive hot stars have lifetimes too short for biological evolution. Very small, cool stars have habitable zones so close that planets become tidally locked and suffer extreme stellar flares. Binary star systems with close stellar companions have unstable planetary orbits. The suitable candidates are roughly Sun-like stars in the spectral range F, G, and K, which constitute only about 15 to 20% of all stars. Furthermore, not all suitable stars have Earth-like planets in their habitable zones. Based on Kepler mission data, perhaps 20 to 40% of Sun-like stars have terrestrial planets in the habitable zone where liquid water can exist on the surface. Combining these factors means that perhaps 3 to 8% of all stars are Sun-like stars with potentially habitable planets. In our region of the galaxy, with roughly 200 to 400 billion total stars, that's 6 to 32 billion potentially habitable star systems. But these are distributed across the entire galactic volume with average separation of perhaps 30 to 100 light years rather than the 5 light year average for all stars. So the distances relevant for galactic colonization targeting habitable planets are not the 5 light years to nearest neighboring stars, but rather tens to hundreds of light years to nearest potentially habitable systems and thousands to tens of thousands of light years to reach across significant portions of the galaxy, establishing widespread presence. If a civilization wanted to colonize just 1% of the galaxy's habitable systems, meaning perhaps 60 to 320 million star systems, they'd need to reach destinations spread across 1,000 seconds to 10,000 seconds of light years from their origin, requiring an enormous number of missions to different targets at vast distances. The speed at which spacecraft can travel determines how long these journeys take, and here we encounter both fundamental physical limits and practical engineering constraints that severely restrict achievable velocities. The absolute speed limit is the speed of light at 300,000 kilometers per second. Nothing with mass can reach or exceed this speed according to special relativity. As objects with mass approach light speed, their relativistic mass increases toward infinity, requiring infinite energy to reach exactly c. Practical spacecraft must travel at some fraction of light speed, with the fraction determined by available energy and propulsion technology. Current spacecraft, using chemical or ion propulsion, achieve velocities of roughly 10 to 40 kilometers per second relative to the Sun. This is about 0.00000, 3c to 0.00013c. At these speeds, reaching Alpha Centauri 4.4 light years away would take 30,000 to 130,000 years. Reaching destinations 1,000 light years away would take 7 to 30 million years. These timescales are far longer than any biological organism or civilization could survive, making interstellar colonization completely impractical with current propulsion technology. We must consider advanced propulsion concepts that could potentially achieve higher velocities. Nuclear pulse propulsion, using sequential nuclear explosions to push spacecraft, was studied in Project Orion in the 1,950 seconds, 1,960 seconds. Theoretical studies suggested this could achieve velocities around 0, 3c to 0, 1c, or roughly 10,000 to 30,000 kilometers per second at 0. 1c reaching Alpha Centauri would take 44 years, and reaching 1,000 light years would take 10,000 years. This is substantial improvement. But the technology was never developed beyond paper studies and faces enormous engineering challenges, including containing nuclear explosions, managing radiation, and achieving the enormous mass ratios needed for high delta V. Fusion propulsion, using controlled fusion reactions to produce thrust, has been proposed in various forms. If fusion can be achieved with high efficiency and high exhaust velocity, it might enable speeds around 0.1c to 0.2c. This would reduce journey times to nearby stars to decades, and to distant stars to thousands or tens of thousands of years. but controlled fusion for power generation remains elusive after 70 years of research, and fusion propulsion for spacecraft is even more speculative, requiring breakthroughs in plasma confinement and neutron management and fuel handling that might never be achieved. Antimatter propulsion using matter-antimatter annihilation to produce energy could theoretically achieve very high exhaust velocities, potentially enabling spacecraft velocities of 0, 3c to 0, 9c at 0. 5c, reaching 1,000 light years, would take 2,000 years, and crossing the galaxy would take 200,000 years. These timescales are still extraordinarily long, but start to approach what might be conceivable for multi-generational missions or suspended animation scenarios. However, antimatter propulsion faces fundamental barriers that likely make it forever impractical. The first barrier is antimatter production. Antimatter doesn't exist naturally in significant quantities and must be manufactured by converting enormous amounts of energy into antimatter particles through particle accelerators. Current production rates are measured in nanograms per year at costs of roughly $60 trillion per gram. A spacecraft requiring tons of antimatter fuel would need production capabilities millions or billions of times beyond anything remotely feasible. Even with revolutionary improvements in production efficiency, the energy costs of creating antimatter are fundamental, not just engineering challenges. The second barrier is antimatter storage. Antimatter annihilates instantly upon contact with normal matter, releasing enormous energy. Storing antimatter requires perfect isolation in vacuum using magnetic or electric fields to suspend the particles away from container walls. Any containment failure causes instant annihilation, potentially destroying the spacecraft. Maintaining perfect containment for decades or centuries during interstellar flight, while systems degrade from radiation and wear, seems nearly impossible. The failure probability over such timescales approaches certainty. The third barrier is propulsion efficiency. Even if you have antimatter fuel and can store it, using the annihilation energy for propulsion is extremely difficult. Matter-antimatter annihilation produces high-energy gamma rays and particle jets that are difficult to direct for thrust. Most proposed designs have very low efficiency, converting annihilation energy to directed thrust, and the gamma radiation poses severe challenges for spacecraft structure and payload protection. Realistic antimatter drives might achieve much lower velocities than theoretical maximum because of these inefficiencies. So, examining realistic propulsion options, we find that velocities above about 0, 1c to 0, 2c are extraordinarily difficult, and velocities approaching 0, 5c to 0, 9c are probably impossible with any feasible technology. This means that crossing 1,000 light years requires, at minimum, 5,000 to 10,000 years, and crossing significant portions of the galaxy requires 50,000 to 500,000 years, depending on the fraction of light speed achieved and the specific destinations. These timescales are the fundamental constraint within which all other challenges must be solved. Now let me examine in comprehensive detail the radiation environment in interstellar space and why it makes galactic travel absolutely lethal for biological organisms over the extreme timescales required. Because cosmic radiation is not merely a challenge to be engineered around, but is a fundamental barrier that guarantees biological death during journeys lasting thousands to hundreds of thousands of years. The radiation environment in interstellar space is dominated by galactic cosmic rays, which are high-energy particles, primarily protons and heavier nuclei, accelerated to near light speed by supernova explosions and other violent astrophysical processes. These particles have energies ranging from millions to billions of electron volts traveling through the galaxy and permeating all of interstellar space with no shielding available. The flux of galactic cosmic rays in interstellar space away from stellar systems is roughly 3 to 5 particles per square centimeter per second, with energies typically between 100 million and several billion electron volts. This might sound like small number, but integrated over the surface area of a spacecraft and over thousands of years, the cumulative particle fluence becomes enormous. A spacecraft with 100 square meter surface area receives about 30,000 to 50,000 cosmic ray impacts per second, or roughly 1 to 1.6 trillion impacts per year, or 1 to 1.6 quadrillion impacts per 1,000 years. These particles penetrate deep into materials and cannot be effectively shielded against. The biological damage from cosmic radiation comes from the ionization these high energy particles cause when passing through tissue. Each particle creates track of ionization along its path, breaking chemical bonds and damaging molecules including DNA, proteins, and cellular structures. The most serious damage is to DNA, where ionization causes single-strand and double-strand breaks that can lead to mutations or cell death. The body has repair mechanisms for radiation damage, but these mechanisms can be overwhelmed by high doses and become less effective over time as damage accumulates and repair systems themselves are damaged. The dose rate from galactic cosmic rays in interstellar space is approximately 0.4 to 0.6 grays per year, or roughly 400 to 600 millisieverts per year, using quality factors to account for the higher biological effectiveness of heavy ions compared to gamma rays. This is about 100 to 200 times higher than natural background radiation on Earth's surface, which is roughly 2 to 3 millisieverts per year. It's also about 2 to 4 times higher than radiation doses that astronauts on Mars' surface would receive, which are about 200 to 300 millisieverts per year, because Mars has thin atmosphere, providing some shielding. For a journey lasting 10,000 years at zero, 1C to reach a destination 1,000 light years away, the cumulative radiation dose would be approximately 4,000 to 6,000 grays, or 4 to 6 million millisieverts. To put this in perspective, acute radiation doses above about 5 to 10 grays cause death in humans within weeks from radiation sickness. Doses of 100 grays cause death within hours. The dose from 10,000-year journey is 400 to 600 times the immediately lethal acute dose. Even spread over thousands of years, this cumulative dose is absolutely fatal, causing catastrophic damage to all biological systems. The damage mechanisms are multiple and reinforce each other. Direct DNA damage causes mutations and cell death at rates that exceed repair capacity. Somatic cells accumulate damage, leading to tissue degradation and organ failure. Stem cell populations are depleted, preventing tissue regeneration. The central nervous system experiences neuron death and cognitive decline. The cardiovascular system develops accelerated atherosclerosis and heart disease. The immune system becomes progressively less functional, increasing susceptibility to infections and cancer. Cancer rates increase dramatically as damaged cells lose growth control mechanisms. The reproductive system experiences damage to germ cells, causing sterility and genetic damage to offspring if reproduction occurs. The timescale of damage accumulation means that even if organisms start the journey healthy, they progressively deteriorate over centuries and millennia. There's no steady state where damage is balanced by repair, because the damage rate exceeds repair capacity, and repair systems themselves degrade over time. Mathematical modeling of radiation damage accumulation shows that biological organisms have finite radiation tolerance measured in tens to hundreds of grays before irreversible fatal damage occurs. The doses from interstellar journeys exceed tolerance by factors of hundreds to thousands, guaranteeing death. Shielding cannot solve the radiation problem, because the most energetic cosmic rays penetrate any practical amount of shielding material. Cosmic rays with energies above 1 GeV, billion electron volts, require meters to tens of meters of shielding material to significantly reduce their intensity. A spacecraft with 10 meters of water shielding around the crew compartment would have mass of roughly 30,000 to 100,000 tons, depending on configuration. This is far beyond what can be accelerated to relativistic speeds with any conceivable propulsion system. The mass ratios would be prohibitive, making the mission impossible. Even if massive shielding could somehow be accelerated, it only partially reduces radiation dose rather than eliminating it. 10 meters of water might reduce dose rate by a factor of 10 from 500 millisieverts per year to 50 millisieverts per year. This is improvement. But over a 10,000-year journey, the cumulative dose is still 500,000 millisieverts, or 500 grays, still about 50 to 100 times the acute lethal dose, and far above the cumulative tolerance for biological survival. You'd need shielding measured in hundreds of meters to reduce dose rates to Earth-like levels, which would require millions of tons of mass. Furthermore, shielding itself creates secondary radiation problems through nuclear interactions. When high-energy cosmic rays strike shielding nuclei, they produce cascades of secondary particles, including neutrons and pions and gamma rays. These secondaries can be even more damaging biologically than primary cosmic rays in some energy ranges. This means that adding shielding doesn't simply reduce dose in proportion to thickness, but creates complex trade-offs where you must optimize shielding thickness and composition to minimize total dose, including secondaries. Even optimized shielding provides only modest dose reduction factors. Active shielding using magnetic or electric fields to deflect charged particles has been proposed but faces severe limitations. The cosmic rays that penetrate deepest and are hardest to shield are the highest energy particles, which require enormous field strengths to deflect measurably, creating magnetic fields strong enough to deflect GeV energy protons, requires superconducting magnets with field strengths of several Tesla extending over hundreds of meters. The mass and power requirements for such systems are prohibitive for spacecraft, and magnetic fields don't deflect neutral particles or gamma rays, which are significant contributors to radiation dose. So, examining radiation exposure in detail reveals it as absolute barrier to biological survival during galactic crossing. The cumulative doses over thousands to hundreds of thousands of years exceed biological tolerance by factors of hundreds to thousands. No amount of shielding that can practically be implemented reduces doses to survivable levels over such timescales. The radiation damage is progressive and irreversible, leading to certain death. Any biological organism attempting galactic crossing will die from radiation poisoning long before reaching destinations thousands of light years away, regardless of what other systems work perfectly. Now let me examine the spacecraft reliability challenges that compound the radiation problem. Because even if we could somehow solve the biological radiation damage through speculative technologies like continuous cellular repair or tissue regeneration, the spacecraft systems themselves cannot maintain function for thousands to millions of years required for galactic crossing. Mechanical and electronic systems degrade and fail on timescales far shorter than interstellar journey durations, creating mathematical certainty of catastrophic system failures that kill the crew or prevent mission completion. Modern spacecraft are designed for operational lifetimes measured in years to decades at most. The Voyager probes launched in 1977 have been operating for about 45 years and are beginning to fail, with instruments shutting down and power declining. The longest operating satellites in Earth orbit have lifetimes of 20 to 30 years before systems degrade enough to end missions. The International Space Station requires constant maintenance and regular resupply of replacement parts to remain operational, despite being in relatively benign environment of low Earth orbit just 400 kilometers from Earth. These examples represent the upper limit of current engineering for spacecraft longevity at timescales of decades, not millennia. The failure modes for spacecraft systems are numerous and cumulative. Mechanical components like valves and pumps and motors experience wear from moving parts and eventually seize or leak. Seals and gaskets degrade from radiation and thermal cycling, allowing leaks. Electronic components fail from radiation damage, causing single-event upsets and gradual degradation of semiconductor devices. Solar panels degrade from radiation, reducing power output typically by 30 to 50% over decades. Batteries lose capacity and eventually fail. Propulsion systems develop leaks or clogs or corrosion in fuel lines and engines. Structural materials develop fatigue, cracks from thermal cycling, and micrometeorite impacts. Sensors drift out of calibration or fail completely. The reliability mathematics of complex systems shows that even if individual components have high reliability, the system reliability decreases exponentially with mission, duration, and with number of components. If a spacecraft has 10,000 critical components, each with 99, 9% probability of functioning for 1 year, the probability that all components function for 1 year is 0.999. 10,000 is approximately equal to 0.00005, or about 0.005%, essentially zero. Maintaining system function requires redundancy, where backup components take over when primary components fail. But redundancy only delays eventual failure if you have 3 redundant systems, each with 99.9% annual reliability. The probability that at least one functions for 1 year is 0.03, is approximately equal to 0.999999999, or about 99.9999999%, very high. But the probability that at least one functions for 1,000 years is much lower because failures accumulate and eventually all redundant systems fail. Over very long timescales, all redundant systems are exhausted and the spacecraft becomes non-functional. The mathematics shows that achieving high reliability over thousands of years requires either impossibly high component reliability or enormous amounts of redundancy, adding mass and complexity. Maintenance and repair could extend system lifetime indefinitely in principle if crew can diagnose failures and replace failed components with spares. The spacecraft can continue functioning as long as spare parts are available, but maintenance requires access to components and tools and replacement parts and trained personnel. For interstellar missions lasting thousands of years, the quantity of spare parts needed to replace all critical components multiple times would add enormous mass to the spacecraft. And even with spares, eventually you run out or encounter failures that cannot be repaired with available parts. The required reliability for unmaintained systems can be calculated from mission duration and acceptable failure probability. If we want 90% probability that spacecraft systems function for 10,000-year journey and the spacecraft has 1,000 critical subsystems, each subsystem must have reliability R, where R 1,000 is greater than or equal to 0.9 for 10,000 years. This requires R is greater than or equal to 0.9, 1 over 1, 0, 0, 0, is approximately equal to 0.9999, or 99.99% reliability over 10,000 years per subsystem. This means each subsystem can have failure probability of only 0.01% over 10,000 years, which is extraordinarily difficult to achieve. Converting to failure rates, this requires subsystem failure rate of less than 0.00001% per year, or about 10, -7 failures per year per subsystem. This is 10 to 100 times better than typical aerospace component failure rates. Achieving such reliability requires either revolutionary improvements in component design and materials or enormous testing programs to screen out defective components. But testing for 10,000-year reliability would require 10,000 years, which is impractical. We cannot verify that components will last 10,000 years without actually waiting 10,000 years. The radiation environment in interstellar space actively degrades spacecraft systems, accelerating failures, electronics are particularly vulnerable to radiation, with semiconductors experiencing gradual degradation from accumulated dose and sudden failures from single event effects where cosmic ray impacts cause data corruption or circuit burnout. Radiation-hardened electronics have better tolerance, but still degrade over time and are heavier and more expensive and less capable than commercial electronics. Maintaining electronic systems for thousands of years in interstellar radiation environment is extraordinarily challenging. Materials also degrade from radiation exposure. Polymers and plastics become brittle and crack. Lubricants break down, losing their lubricating properties, causing mechanical components to seize. Solder joints develop cracks from thermal cycling and radiation damage. Structural materials experience radiation-induced embrittlement, reducing fracture toughness. Optical materials like windows and lenses darken from color centers created by radiation, reducing light transmission. All these degradation processes are cumulative and progressive, eventually leading to system failures. So examining spacecraft reliability, we find that maintaining complex systems functional for thousands to hundreds of thousands of years is effectively impossible with any realistic technology. Failure rates and degradation processes guarantee that systems will fail catastrophically long before completing galactic crossing, even with extensive redundancy and maintenance and repair. The timescales exceed what can be achieved. Spacecraft attempting galactic travel will experience cascading system failures, leading to loss of life support or propulsion or navigation, or power, causing mission failure and crew death. Now, let me examine the biological preservation challenges for scenarios where the crew is not kept awake for the entire journey, but instead uses some form of suspended animation or cryogenic preservation to survive the extreme timescales. Because this is often proposed as solution to both the radiation damage and the psychological problems of conscious multimillennial journeys. But biological preservation faces its own severe barriers that make it impossible for journeys lasting thousands to hundreds of thousands of years. The concept of suspended animation involves slowing or stopping biological metabolism to prevent aging and reduce resource consumption during long journeys. Various approaches have been proposed, including therapeutic hypothermia, reducing body temperature to slow metabolism, cryogenic freezing at liquid nitrogen temperatures to stop metabolism completely, or chemical preservation using vitrification to prevent ice crystal formation. The goal is to preserve the organism in quasi-stable state during transit and then revive it at the destination. This sounds conceptually feasible, but faces enormous practical challenges. Therapeutic hypothermia, reducing body temperature to around 10 to 15 degrees Celsius, can slow metabolism by factors of 3 to 5 and has been used medically for up to several days. But maintaining hypothermia for years or decades causes severe problems, including cardiac dysfunction and blood clotting and immunosuppression and increased infection risk. The longest documented survival in hypothermic state is days, not years. Extending to months or years appears impossible with current understanding because biological systems continue to function slowly and develop problems even at reduced temperature. Furthermore, hypothermia doesn't stop radiation damage, but only slows biological repair mechanisms. The radiation continues to damage DNA and proteins and cellular structures at the same rate, regardless of body temperature. But the repair mechanisms are slower at reduced temperature, meaning damage accumulates faster relative to repair. This actually makes radiation damage worse in hypothermic state than in normal active state, where repair mechanisms function optimally. So hypothermia makes radiation problem worse, not better. Cryogenic freezing at temperatures around negative 196 degrees Celsius using liquid nitrogen stops all biological metabolism and preserves tissue indefinitely. In principle, small organisms like nematode worms and human embryos can be frozen and revived successfully using cryoprotectants to prevent ice crystal formation. But scaling to large multicellular organisms like humans faces severe challenges that have never been overcome despite decades of research in cryobiology. The primary problem is that freezing large volumes of tissue without ice crystal formation requires very rapid cooling rates that are impossible to achieve in large organs. When water freezes, it forms ice crystals that puncture cell membranes and damage cellular structures, causing death when thawed. Cryoprotectant chemicals can prevent ice formation through vitrification, where the solution solidifies into glass-like state without crystals, but cryoprotectants must penetrate all tissues rapidly and uniformly. In large organs, the time required for cryoprotectants to diffuse to the core is long enough that toxicity damages the tissue before it can be frozen. Achieving uniform vitrification of whole humans or large animals has never been demonstrated. Even if vitrification is achieved, the storage at cryogenic temperatures faces challenges over long time scales. At temperatures around -196 degrees Celsius, molecular motion is greatly slowed but not completely stopped. Radiation damage still accumulates through ionization events that break chemical bonds, even in frozen tissue. Over thousands of years, the cumulative radiation dose at interstellar radiation levels would cause extensive damage to frozen tissue. DNA would accumulate strand breaks and base modifications. Proteins would experience radiation-induced cross-linking and fragmentation. Lipid membranes would degrade. The background radiation dose rate in interstellar space of 400 to 600 millisieverts per year means that frozen tissue would receive cumulative dose of 4,000 to 6,000 grays over 10,000 years. Even while frozen, this dose causes extensive damage to biomolecules even without active metabolism. Studies of radiation effects on frozen biological materials show significant damage at doses above 10 to 100 grays. The doses from interstellar travel are 40 to 600 times higher and would completely destroy the molecular structures needed for revival. Frozen organisms would essentially be chemically degraded into non-viable tissue. Furthermore, the cryogenic storage system itself must function reliably for thousands to hundreds of thousands of years, maintaining constant temperature without failures. Any warming above about -130 degrees Celsius causes ice crystal formation and tissue destruction. Maintaining cryogenic temperatures requires continuous refrigeration using cryocoolers or continuous supply of cryogenic fluids like liquid nitrogen or liquid helium. These systems consume power and have mechanical components that degrade and fail over 1,000-year timescales. The probability of cooling system failure approaches certainty. If cooling fails and tissue warms even briefly, the cryoprotectants become toxic at higher temperatures and cause chemical damage. Ice crystal formation destroys cellular structures. The organism dies and cannot be revived. The reliability requirements for cryogenic systems over millennia are even more stringent than for other spacecraft systems because any failure is instantly fatal with no possibility of recovery. You cannot repair cryogenic freezer after organisms have thawed and died. The entire mission is lost with single system failure. Alternative preservation approaches like chemical fixation or plastination permanently alter tissue in ways that are incompatible with revival. These might preserve gross anatomical structures, but they destroy the molecular machinery needed for life, including functional proteins and nucleic acids. Organisms preserved by these methods cannot be revived by any known or conceivable process. They're essentially permanently dead. Even though their structures are preserved, this makes them useless for transporting living organisms across interstellar distances. So examining biological preservation methods in detail reveals that none can maintain viable organisms over the thousands to hundreds of thousands of years required for galactic crossing. Suspended animation slows but doesn't stop aging and makes radiation damage worse. Cryogenic freezing might preserve tissue briefly but accumulates radiation damage over millennia that destroys viability, and cryogenic system reliability requirements over such timescales cannot be met. Any organisms placed in suspended animation or cryogenic preservation for galactic journey will be dead long before arrival, either from accumulated radiation damage or from preservation system failures. Now let me examine the alternative scenarios that are sometimes proposed to circumvent the biological limitations I've described, because advocates of galactic colonization often retreat to speculative scenarios involving generation ships or uploaded consciousness or self-replicating probes when confronted with the impossibility of preserving individual organisms across galactic distances. But each of these alternatives faces its own severe barriers that make them equally or more impossible than straightforward interstellar travel with preserved crews. Understanding why these alternatives fail is essential for recognizing that the impossibility of galactic travel is not just about current technological limitations, but about fundamental constraints that cannot be overcome through clever mission architecture or future breakthroughs. The generation ship concept proposes that instead of preserving individual organisms for the entire journey, you maintain a breeding population of organisms across many generations during the voyage. The initial crew reproduces, and their children take over operating the ship and reproduce in turn, creating continuous chain of generations from launch to arrival. This supposedly solves both the radiation damage problem by allowing natural replacement of damaged cells and tissues through reproduction, and the psychological problem by providing social structures and sense of purpose through multi-generational society. Generation ships appear in countless science fiction stories as the solution to interstellar travel. But generation ships face catastrophic problems that make them fundamentally unworkable for journeys lasting thousands to hundreds of thousands of years. The first problem is genetic degradation from radiation and small population effects. As I've discussed, the radiation dose rate in interstellar space is about 400 to 600 millisieverts per year, which causes extensive DNA damage in reproductive cells as well as somatic cells. This damage is passed to offspring through mutations in germ cells. The mutation rate in irradiated populations would be far higher than natural mutation rates, leading to accumulation of deleterious mutations over generations. Genetic modeling shows that small populations accumulate harmful mutations through a process called Muller's ratchet, where deleterious mutations become fixed in the population because the population is too small for natural selection. To efficiently remove them, the minimum viable population size to avoid genetic degradation in normal Earth radiation environment is estimated at several hundred to a few thousand individuals, depending on generation time and selective pressure. But in the high radiation environment of interstellar space, the mutation rate is 100 to 200 times higher than on Earth, dramatically increasing the population size needed to maintain genetic health. Realistic calculations suggest that maintaining genetic viability over 1,000 generations in interstellar radiation environment would require populations of tens of thousands to hundreds of thousands of individuals to provide enough genetic diversity for selection, to remove harmful mutations, and to buffer against random genetic drift. A generation ship housing 100,000 people for a 10,000-year journey would require enormous spacecraft massing millions of tons with life support and agriculture and living space. The propulsion requirements make this completely impossible to accelerate to relativistic speeds. Even if you could somehow launch such massive population, the second problem is maintaining viable ecology for thousands of generations. The population requires food production, which requires agricultural systems, which require recycling of nutrients and water and waste. These ecological systems must remain stable and productive for the entire journey, providing all nutritional needs without external inputs. As I've discussed in previous contexts, closed ecological systems are extraordinarily difficult to maintain and prone to instabilities and failures. The biosphere, to experiment on Earth, failed to maintain closure for just 2 years, despite being on Earth with access to external resources. Scaling closed ecology to tens of thousands of people for thousands of years makes stability problems far worse, Crop diseases or pest outbreaks could destroy food production, causing famine. Nutrient cycling imbalances could lead to accumulating deficiencies or toxicities, making soil unproductive. Microbial ecology could shift in ways that interfere with waste decomposition or nutrient processing. Genetic drift in agricultural crops and livestock over thousands of generations could reduce productivity or nutritional quality. Any of these ecological failures would cause collapse of the food system, leading to mass starvation and mission failure. The third problem is social stability over thousands of generations in confined environment. Human societies confined to spacecraft with no frontier and no expansion would develop severe social pathologies from overcrowding and resource competition and lack of opportunity. Historical examples of isolated communities like Easter Island or Norse Greenland show that societies confined to limited resources tend toward resource depletion and social collapse and violence. Generation ships would face even more extreme confinement with absolutely no possibility of expansion or external trade. The social dynamics would likely tend toward either rigid authoritarianism, where central authority strictly controls reproduction and resource allocation to prevent overpopulation and overexploitation, or toward anarchic breakdown, where factions fight for limited resources. Both outcomes are incompatible with maintaining complex technological systems like spacecraft. Authoritarian regimes tend to suppress innovation and maintain control through limiting knowledge, making them unable to solve novel technical problems. Anarchic societies cannot maintain the cooperation needed for spacecraft operations. Either way, the society would eventually lose capability to operate the spacecraft, leading to system failures and death. The fourth problem is cultural and knowledge maintenance. Over thousands of generations, the crew must maintain technical knowledge needed to operate and repair spacecraft systems, including advanced physics and engineering and computer science and material science. They must pass this knowledge across generations through education, but in confined society with limited resources, maintaining comprehensive education system is difficult. Specialized knowledge that's not immediately useful might be forgotten as generations pass. If critical knowledge is lost, the crew loses ability to maintain systems and the spacecraft fails. Furthermore, the initial mission purpose of reaching distant star system might be forgotten or rejected by later generations who were born on the ship and never chose to participate in the mission. Descendants 500 generations after launch have no connection to the original mission planners and might question why they should continue toward destination their ancestors chose. They might decide to alter course or abandon the mission or develop cultural practices incompatible with spacecraft operations. Maintaining cultural continuity and commitment to mission across thousands of generations seems psychologically and sociologically implausible. The fifth problem is that generation ships don't actually solve the radiation problem as claimed. Yes, the population can reproduce, replacing individuals as they die from radiation damage and aging, but the radiation still causes extensive damage to the population. Cancer rates would be enormously elevated, with perhaps 50 to 90% of the population developing cancer at some point in their lives. Many would die from radiation-induced diseases before reaching reproductive age, reducing population viability. Those who do reproduce pass genetic damage to offspring, degrading the gene pool. Over thousands of generations, the cumulative genetic damage would make the population increasingly sickly and short-lived until it can no longer maintain itself. Radiation shielding for generation ships faces the same mass constraints as for other spacecraft. Providing adequate shielding for population of tens of thousands requires millions of tons of shielding material that cannot be accelerated to relativistic speeds with any plausible propulsion. Realistic generation ships would accept high radiation exposure throughout the journey, accepting that the population would suffer severe health consequences. This makes the mission even more ethically problematic because you're condemning thousands of generations to live short, painful lives ravaged by radiation-induced disease for mission they didn't choose. So generation ships don't solve the problems of galactic crossing, but actually make them worse by introducing additional failure modes related to population genetics and ecology and social stability and cultural continuity. The timescales of thousands to hundreds of thousands of years are far too long for any biological population to maintain itself in spacecraft environment, even with reproduction. Generation ships are not a feasible solution to galactic travel, but are another impossible scenario. The concept of uploaded consciousness proposes avoiding biological limitations entirely by transferring minds to digital substrates that can survive indefinitely and don't suffer radiation damage or require life support. The idea is to scan human brains at sufficient resolution to capture all the information that constitutes consciousness and personality, then run this information as software on computers. The uploaded minds could then travel across the galaxy in small, lightweight spacecraft without the burdens of biology. Upon reaching destination, they could download into new biological bodies grown from stored genetic information or continue existing as digital entities. This scenario is popular in science fiction and transhumanist speculation and is sometimes presented as inevitable future development, but it faces fundamental problems that make it either impossible or irrelevant to the question of biological species crossing the galaxy. The first problem is that we have no idea whether consciousness can be uploaded at all. Consciousness might require specific biological substrates that cannot be replicated in silicon. The relationship between brain structure and subjective experience is not understood well enough to know whether scanning neural connectivity preserves the essential features that create consciousness. Even if consciousness can in principle be uploaded, the technical requirements for scanning brains at adequate resolution are staggering. To capture all relevant information, you'd need to map the positions and connection strengths of approximately 86 billion neurons and 100 trillion synapses, along with the molecular states of neurotransmitters and ion channels. And modulatory systems, this might require atomic scale imaging of entire brains, which is far beyond current or foreseeable imaging technology. Destructive scanning that slices the brain into thin sections might be possible, but this kills the original person raising questions about whether the upload is continuation of original consciousness or merely a copy. Furthermore, even if scanning is possible and uploads can be conscious, calling this humans crossing the galaxy is questionable when the travelers are software running on computers, not biological humans. If we're willing to accept digital entities as continuation of humanity, then we're not talking about biological species crossing the galaxy, but about post-biological artificial intelligence spreading through the galaxy, which is a completely different scenario. The original question is whether biological species can cross the galaxy, and uploading doesn't solve this, but rather abandons biology entirely. The uploads themselves would still face challenges during galactic crossing, even though they're not biological. Computers are vulnerable to radiation damage causing bit flips and memory corruption and processor failures. Radiation-hardened computers exist but are heavier and less powerful than commercial processors and still accumulate damage over time. Maintaining computational systems functional for hundreds of thousands of years in interstellar radiation environment is difficult. And if the hardware fails, the uploaded minds are lost, just as biological organisms die when their bodies fail. The concept of growing biological bodies at the destination for uploads to download into requires solving all the problems of biological preservation and development. You must either transport frozen embryos or eggs and sperm, which face the radiation damage problems I've discussed, or you must transport complete DNA sequences as digital information and synthesize organisms from scratch at the destination, which requires capabilities far beyond current biotechnology and might never be possible. Growing adult bodies from genetic information requires recapitulating entire development from embryo through fetus, through infant, through child, through adult, which takes decades and requires resources and expertise that might not be available at the destination. So uploading consciousness doesn't solve the problem of biological species crossing the galaxy, but rather redefines the problem to be about digital entities crossing the galaxy. If we're asking whether biological organisms specifically can cross the galaxy, the answer remains no, because uploading abandons biology. If we're asking whether some descendant of humanity, regardless of substrate, can cross the galaxy, then we're asking a different question that might have different answer but isn't what we originally meant by species crossing, the galaxy. The concept of self-replicating probes, or von Neumann probes, proposes sending small unmanned spacecraft that travel to distant star systems and upon arrival use local resources to build copies of themselves, which then launch to further star systems. This creates exponential expansion, where one probe becomes 2, becomes 4, becomes 8, in successive generations, eventually covering the entire galaxy. Because probes are unmanned and small, they can be accelerated to higher speeds and don't require life support. This is sometimes presented as inevitable expansion strategy for any advanced civilization. But self-replicating probes face severe limitations that prevent them from functioning as mechanism for biological species to cross the galaxy. First and most obviously, they don't actually transport biological organisms, but only carry information. A probe arriving at distant star system could in principle carry genetic information or uploaded minds that could be used to recreate organisms or conscious entities. But as I've discussed, this faces all the problems of biological recreation or uploading. Carrying frozen organisms faces radiation damage problems. Carrying only information requires capabilities we don't have and might never have. Second,